Okay, this is part 2 of section 4.8, dealing with Newton's method. I need to pick up with the computing f prime of x of n. And of course, x of n was ln of 5. So here I use negative 3e to the negative x of n minus 14. So in this case here, I'll do negative 3 for the e, second ln, and press the negative key. And then your x of n is ln of 5. So I press ln and then 5, close parentheses, use the right arrow key to get out of it, and then minus 14. So here I ended up with negative 14.6. So f prime of x of n is negative 14.6. Now, to get this value, f of x of n divided by f prime of x of n, I would divide this f of x of n by f prime of x of n. So I'm going to go and type in the whole thing as is, negative 21.932931 divided by negative 14.6. That would give me 1.50. Actually, I think, I'm going to see if I can type in that negative 21.93213077 and divide that by negative 14.6. Because I guess in the notes that I did, I used all the numbers there. Okay, there we go. I used all of the numbers there on that screen. Now, for this one, it will be 1.502201 if I was to round that to 6 decimal places. In this case, I was using all the numbers that were on that screen for this amount in order to get a better value of this. All right, so now to get this last one right here, x of n minus f of x of n divided by f prime of x of n. Here's x of n, and I'm going to subtract this from ln of 5. So if I do ln 5, close parentheses, minus, and I'm going to pull up this answer that I got right here. So I'm going to do second and the negative key at the bottom for that previous answer, because it's going to take that previous answer and subtract from it ln of 5. So here I'm going to get, let's say the 6 decimal places in this case, 1.07237. Okay. All right, so now I need x of 2. So in this case here, this right here is x of 1. So your n is going to be 1 here. And for x of n, it's going to be this number right here. So I'm going to take that number and let that be your new x of n. That's going to be your new approximation. And then we're going to find out what f prime of x of n is going to be. All right, so here's what I'm going to do here. This is f of x of n, which is 3e to the negative x of n minus 14 times x of n. So I use that for 3, and then second ln for the e, and then negative. Your x of n is now that negative, is now that 1.07237. And I think I can pull that answer up by doing second and negative for the answer. And then minus 14. And then left parentheses, second negative for that answer. And I'm taking that previous answer and just trying to come up with a better approximate value for f of x of n, which is going to be, in this case, 1.193617. If that was rounded to 6 decimal places. 1.193617. Okay. And then for f prime of x of n, that's going to be that value right there. That's going to be that expression here. So here I'm going to have -3, and then second, and then the e, and then press the negative key because they're negative. That x of n was, I'm going back to here, and I'm going to go ahead and enter that value as is, 0.10723711748. Then use my right arrow key to get out of the exponential part, then -14. So the 6 decimal place, this will be negative 16.69493.8. $6.4938. So that's that. All right, now divide this number by this number, and that would give you f of x of n divided by f prime of x of n, what that value would be. Okay, so in this case here, I'm going to take this previous number, type that in as is, divide that by the previous answer, second, and negative key for that answer. Let's see what we come up with. That's going to be a negative 0.071496, rounded to 6 decimal places. So let me move this over and fill in that answer, negative 0.071496. And then finally, to get x of n minus f of x of n divided by x of n, well, x of n was this number right here, 1.07237. That's going to be minus this number right here. So 0.107237, and then minus this previous answer. I can just say second and negative key for the answer. And this will be to, let's say, 6 decimal places, 0.178733. And that's all that we were looking for here. So in this case here, x1, the first iteration there was 0.107237. That was to 6 decimal places. And then x2 came out to be 0.178733. Okay. So those are the approximations for x1 and x2. Okay. Now, here I had to use a chart by breaking up that formula that we were using for Newton's method, which is, of course, the x of n plus 1 equaling to x of n minus f of x of n divided by x of n, f prime of x of n. Because the x of n was this column, f of x of sub n was this column here, and then f prime of x of n was this column. Then we had to divide these two, that made up this column, subtract this from this to get the final column. Okay. All right, now I'm going to show you how to use a calculator to come up with your iterations here, because some cases you may have to do many iterations here. Like in this example, let's say we're going to use a calculator or program to compute the first 10 iterations of Newton's method when they are applied to the following function with the given initial approximation. So in this case here, we got f of x is equal to x squared minus 23. And in this case, x sub 0 is going to be 5. So that tells me n is going to be 0. And then x sub 0, that's going to be 5. So we're looking for the first 10 iterations. That means what I get in this final column starts with x1, x2, x3, x4, x5, x7, x8, x9, and x10. Okay. Now, what I'm going to do here is come up with my formula for Newton's method that I need to use here. Well, if f of x is equal to x squared minus 23, then that means f of x sub n will end up being, replacing the x with x sub n, that'll be x sub n squared minus 23. That will mean f prime of x sub n. I need that. Well, f prime of x, since f of x is equal to x squared minus 23, f prime of x will just simply be 2x. And that will mean f prime of x sub n will be 2 x sub n. So that means x sub n plus 1 will be equal to x sub n minus f of x sub n is that x sub n squared minus 23 divided by f prime of x sub n, that's 2 x sub n. All right, now let me show you how this is going to be done in the calculator. And in this case here, I'm going to have to pretty much give you the keystrokes here. Since x sub 0 is equal to 5, okay? So here x sub 0 is going to be equal to 5. We're going to put that 5 into the calculator and store it in our TI-84 plus calculator. So in this case here, clear this out. Here's the keystrokes. Here I'm going to press the number 5. And then there is a button that says STO on the far left-hand side of your calculator. Here it is, STO. We're going to press that button. And then we're going to store it in X. So we're going to press the XT theta N for the X and then press enter. And it's going to give you the number 5 back. What that means is that the value of the 5 is being stored as the value for X. Okay, now this formula right here, x sub n equaling to x sub n squared, x sub n minus x sub n squared minus 23, that's divided by 2x sub n. This is going to be entered in the calculator. So in this case here, what I'm going to do is put parentheses around x sub n squared minus 23 and parentheses around the 2x. And I'm going to treat those x sub n's like x's, okay? And I do have the keystrokes for that as well. All right, so in this case here, for the x sub n, which was out in front, we have to type in x sub n, and then minus, and then left parentheses, get the xtn for the x, and then press x squared to square it, minus 23. Close parentheses. And then that's going to be divided by, and then the denominator is 2x sub n. So we're going to do left parentheses, 2, and then get the x, and then close parentheses. Then we also have to press the button that says STO to store it, which is down here at the bottom. And then press that xt theta n for the x, and then hit enter. Now, what it's going to do here is giving you the first iteration. Okay, so when you had 0, x of 0 being equal to 5, this value 4.8, when we typed in this, was the value for x of 1. So in this case here, x1 is 4.8. Now, to get the other iterations after that, what I'm going to do here is press enter. And guess what? This value right here represents the second iteration, which is in this case to 6 decimal places, 4.795833. And now to get the third iteration, guess what? I'm going to press enter again. And here's that third iteration, as you can see here, 4.795833 to 6 decimal places. That 1 will make that 5 will make the 1 a 2. So that 4.795832. And then to get the next iteration, I'm going to press enter again. Notice I get the exact same value here. And when that happens, that tells you that you have found the exact value or the exact x-intercept for this function, f of x is equal to x squared minus 23. Okay, you found the exact 0 for this function here. And I can keep pressing enter all the way through and still come up with that same value. Because x5, x6, x7, x8, x9, and x10 will be the same. So that tells me that 4.795831.523 is the 0 of this function, f of x equal to x squared minus 23. Now, of course, if you have questions, you can always reach out to me by email if you need to. But the fact is, you have to know how to enter this in the calculator by just using x's here. We're treating those like x's here. And the numerator, the denominator, you have to put in parentheses. All right, here's one more of these. All right, let's say we have f of x is equal to ln of the quantity x plus 1 minus 3, and our initial approximation is x sub 0 equaling to 19.1. And then we want to find the first 10 iterations of Newton's method when they are applied to the following function. All right, so that means this column represents my iteration starting with x1 all the way through x10. Okay, and what I need in this case here, not only do I need the function, I'm gonna need that the function for Newton's method. Okay, so I have my f of x, but I also need f prime of x. The derivative of ln of x plus 1 would be 1 over x plus 1 times the inside derivative, of course, which will be 1. And then the derivative of minus 3 will be 0. So that's what f prime of x will be. And I'm going to write this at the very bottom. So here my x of n plus 1 is equal to x of n minus f of x of n divided by f prime of x of n. course, if f of x is going to be ln of x, x plus 1 minus 3, then f of x of n, just substitute the x with x of n. This will be ln of x of n plus 1 minus 3. And of course, f prime of x of n will have to be 1 over x of n and then plus 1. So in this case here, I'm going to bring over that x of n minus f of x of n is ln of the quantity x of n plus 1 and then minus 3 divided by f prime of x of n will be 1 over x of n plus 1. All right, now I'm going to simplify this a bit. Okay, what I need to do here is, since I have a complex fraction, notice I have a denominator of x to x of n plus 1. Let's do this. I'm going to multiply the numerator by x of n plus 1 and the denominator by x of n plus 1. Now, when I do that, in the denominator, x of n plus 1 divides out. Then I'm going to have this, x of n minus, and I'm going to put that ln of the quantity x of n plus 1 minus 3 in the bracket. And then that's going to be multiplied by x of n plus 1. And notice I'm going to have a 1 in the denominator, so it will end up being like this. Okay. All right, so here's what I'm going to do here using the calculator. Okay, so I'm going to put this up here so you can see what I'm going to do here. My x of 0 was 19.1. So the first thing I'm going to do here is type in 19.1. I'm going to clear this out, type in 19.1. Press the button that says STO, which is at the bottom, and it's going to give you the right arrow. Then press the xt theta n for the x and then press enter. And it will give you back 19.1. That means that 19.1 will be stored as your value for x. Okay, now what I have here is the keystrokes for this function right here. And actually, the x plus 1 will be on the right side, like I have right here. Notice the x of n plus 1 is on the right side, okay? Now, in this calculator, let me go ahead and rewrite that as this, x of n minus, and then I'm going to put the ln of the quantity x plus 1, and then minus 3, close the bracket, then times x plus 1. Because the way I set it up as these keystrokes is this. Okay, so what we're going to do here is type the x, t theta n for the x, and then minus, then left parentheses, press the ln key, and then get your x by pressing x t theta n for the x, and then plus 1, right parentheses, close that, and then minus 3, and then right parentheses again. Okay, because this bracket represents the parentheses on the outside, and this represents the parentheses on the inside. And then that's going to be multiplied by, so we press the times button, and then left parentheses, xt theta n for your x, plus 1, close parentheses. And then press the button that says STO on the far left-hand side. Press the xt theta n for the x, and then press enter. That will give you the first iteration. So in this case here, since n is going to be 0 and x of n is 19.1. So let me fill this in, 0, and then 19.1. That would mean that your first iteration, x1, would be 19.085532. Because that 1 to the right of it is a 7, that 1 will become a 2. And then to get the next iteration, we press enter again. So now we got 19.085537. And then press enter again. Notice that we come up with the exact same decimal value. Okay, and when that happens, that tells us we do have the exact 0 for this function ln of x plus 1 minus 3. And if I keep pressing enter, I'm going to get the same value here for x4 all the way down to x10. So here, as you pretty much can see that these numbers are going to be converging to an exact 0 for this function. So in this case here, 19.085537 would be the exact 0 for ln of the for f of x equal to ln of x plus 1 minus 3. Now, of course, you could verify this by typing this in the calculator into y1. So if you go to y equal to, press the ln key, and then get your x, then plus 1, close parentheses, minus 3. Let's see if I can do a zoom 6. Okay, now my x of 0 is going to be 19.1. So let me do this. I'm going to change the window, and I'm going to go from 0 up to 20 in increments of 1. So if I do the graph of that, pretty much you're going to see it's getting closer and closer to that x-axis. It's going to cross the x-axis somewhere. Okay, I'll change the window again, 0 to 30, and I'm going to do a scale of 5. Okay, so it is above the x-axis, as you're going to see. But in this case here, to get that 0, of course, you do second and trace for the calculate menu. And I'm going to select menu item number 2 for the 0. So my left bound would be somewhere close to that x-axis, to the point of intersection on the x-axis. I'm going to press enter for left bound, and then for right bound would be somewhere to above it, like right here. And then I have to guess, there's my 0 right here, which is 19.085537, which is exactly what we came up with right here when we were doing Newton's method, okay? Now I'm going to tell you in the homework, they're going to ask for each one of these iterations here, for the first 10 iterations here, saying you have to fill in those values here, and you have to use Newton's method to do this. So I do want to warn you about that, okay? All right, so that does conclude this video on section 4.8, dealing with Newton's method. Feel free to contact me if you have any questions about anything that was presented in this video in part 1 and part 2, and as well as the homework in my math lab.